For decades, physicists believed the universe was playing a trick on them. They could see particles, measure forces, watch matter collide, decay, explode, and transform. Yet something was missing, not a small detail, but the key to existence itself, a mechanism that gives everything mass, a field that permeates the cosmos, and a particle so elusive that entire generations of scientists wondered if it even existed at all. This is the story of the 40-year hunt for the Higgs boson, the so-called God particle, a story of failures, rivalry, collaboration, and the moment humanity finally glimpsed the hidden machinery behind reality. To understand why the Higgs boson mattered, we need to step back into the mid-20th century, when physics was on a roll. Scientists had mapped out electromagnetism, cracked nuclear forces, and discovered a zoo of particles: quarks, leptons, gluons, neutrinos. The Standard Model, a theoretical framework tying all known particles and forces together, was taking shape, but a problem emerged. In the equations describing the fundamental forces, particularly the weak nuclear force, the math predicted that certain particles should have no mass at all, zero. Yet, experiments showed they were heavy, very heavy. Something in nature was giving particles mass, but nothing in the theory could explain how. It was like building a car engine and realizing you forgot to include gasoline. The Standard Model needed a mass-giving mechanism, or the entire thing fell apart. In 1964, a small group of theoretical physicists proposed a radical idea. Peter Higgs in Scotland, François Englert and Robert Brout in Belgium, Gerald Guralnick, Carl Hagen, and Tom Kibble in London, working independently, yet converging on the same answer, described a quantum field that filled all of space. Not empty space, not a vacuum, a field with substance, like an invisible cosmic molasses. When certain particles tried to move through it, they interacted with this field and slowed down. That resistance, at the quantum level, manifested as mass. Lighter particles slipped through easily, heavier particles were dragged more strongly. The idea was bold, elegant, and even poetic. The universe had an underlying medium, a hidden fabric that sculpted the masses of everything from electrons to the W and Z bosons. This new entity became known as the Higgs field, and according to quantum theory, fields always come with particles, small, localized excitations, like ripples on a pond. That ripple would be the Higgs boson. Detecting it would confirm not just the field's existence, but the validity of the entire Standard Model. But there was a problem. Nobody knew how heavy the Higgs boson was. It might have been reachable with existing machines, or it might have required energies far beyond anything Earth could generate. And so began one of the most dramatic scientific hunts in history. The first big push came in the 1980 seconds and 1990 seconds. Labs around the world built enormous particle accelerators, hoping to smash matter with enough force to kick the Higgs boson into existence. CERN's LEP Collider, a 27-kilometer circular machine under the French-Swiss border, fired electrons and positrons together, creating some of the cleanest collision data ever collected. Scientists hoped LEP would be the machine to find the Higgs. They upgraded it, pushed its magnets to their limits, and extended its lifespan again and again. They came agonizingly close. In 2000, signals emerged hinting at a Higgs around 115 GeV, but the evidence wasn't strong enough. LEP had reached its maximum power. The team faced a brutal decision: keep LEP running and risk delaying new experiments by a decade, or shut it down and make way for a machine far more powerful than anything ever conceived. The decision broke hearts, but the future won. LEP was dismantled, the tunnel was cleared, and in its place, CERN began constructing an unprecedented technological monster, the Large Hadron Collider, or LHC. While Europe was preparing for the LHC, the United States had attempted to leap ahead. In Texas, the Superconducting Super Collider, the SSC, was supposed to be the world's largest accelerator, with a circumference 3 times larger than CERN's. It would have dwarfed every scientific instrument ever built. Construction began in the late 1980 seconds, but the project collapsed under political pressure, ballooning costs, and shifting priorities. By the early 1990 seconds, the SSC was dead, leaving the United States sidelined and solidifying CERN as the planet's center of high-energy physics. Had the SSC been completed, the Higgs boson might have been found a decade earlier. Instead, the responsibility now fell entirely on the LHC. The LHC was an engineering marvel. A 27-kilometer ring cooled to colder than outer space, packed with superconducting magnets, powerful enough to steer protons moving at 99.999999% the speed of light. When two proton beams collided, they unleashed energies unseen since the earliest moments after the Big Bang. But high-energy collisions alone weren't enough. To catch the Higgs boson, which decays almost instantly into other particles, CERN needed detectors capable of recording billions of events per second and filtering out the rare, Higgs-like signatures from overwhelming noise. Two enormous detectors rose from the plan, ATLAS and CMS, each the size of a cathedral, packed with thousands of sensors, electronics, and superconducting systems. These detectors weren't just cameras. They were digital time machines, reconstructing subatomic shrapnel into meaningful physics. The hunt officially began in 2010, when the LHC reached the energies needed to produce Higgs particles. But actually finding them was like watching explosions inside a crowded stadium and trying to identify a single firework. A Higgs decays almost instantly, leaving behind patterns of photons, electrons, muons, or quarks, but so do countless other processes. Teams built advanced algorithms, simulations, and filtering pipelines. They combed through petabytes of data. Every day brought false alarms, anomalies, hints, and disappointments. The world waited. Physicists felt the pressure, and the risk was real. The Higgs might not exist at all. If it didn't, the standard model would unravel. A new universe of unknown physics would open, exciting theoretically, but devastating experimentally. Then came the whispers. In late 2011, both ATLAS and CMS began seeing small bumps, statistical excesses, around 125 GeV. Not enough to claim a discovery, but enough to raise eyebrows. Rumors leaked. Press speculation exploded. Physicists stayed cautious. A discovery required a 5 sigma statistical certainty, the equivalent of being 99.99994% sure the signal wasn't a fluke. Years of work came down to a number. The world would have to wait. On July 4th, 2012, representatives from ATLAS and CMS presented their combined results in a packed auditorium at CERN. Peter Higgs himself sat in the front row, quiet, almost trembling. He had once described the Higgs boson as something I never thought would be found in my lifetime. As the graphs appeared on screen, the room erupted. Both experiments independently showed strong, undeniable evidence of a new particle at around 125 GeV. The signal crossed the 5 sigma threshold. It was real. The Higgs boson had been found. Scientists cried. Journalists cheered. Peter Higgs wiped tears from his eyes. Decades of theory, engineering, failure, and relentless optimism had finally paid off. The mass-giving mechanism of the universe was no longer hypothetical, it was experimentally confirmed. Humanity had pulled a thread from the deepest fabric of reality and held it up to the light. But this discovery wasn't the end. It was the beginning of a new era. With the Higgs boson confirmed, physicists now had a tool to probe the boundaries of the standard model. The Higgs itself is strangely light, raising questions about deeper symmetries. Its interactions might reveal clues about dark matter, new particles, or extra dimensions. Some theories predict the Higgs may be connected to the early universe's inflation, the brief moment when the cosmos expanded faster than the speed of light. Others suggest the Higgs could determine the universe's long-term fate, hinting at whether our cosmos is stable or precariously balanced in a false vacuum, ready to collapse trillions of years from now. Yet the discovery also highlighted a profound mystery. The universe shouldn't exist as we know it. According to the Standard Model's equations, quantum fluctuations should have destabilized the vacuum of space shortly after the Big Bang, and yet it didn't. Something prevented the collapse. Something we haven't discovered yet. The Higgs boson, far from tying the final bow on particle physics, revealed cracks in the foundation cracks that may point toward new physics waiting to be uncovered. Today, the LHC continues to smash protons billions of times per second, searching for rare Higgs decays, new particles, and unexplained anomalies. Engineers are upgrading it into the high-luminosity LHC, capable of generating 10 times more collision data. Future colliders, some circular, some linear, some hundreds of kilometers long, are being proposed to study the Higgs with even greater precision, turning it from a trophy discovery into a tool for exploring the unknown. The story of the Higgs is more than a scientific achievement. It's a testament to human persistence. Generations of physicists devoted their careers to searching for something they could not see, could not touch, and were not even sure existed. The journey required global collaboration, political battles, engineering breakthroughs, and theoretical leaps. It required faith in mathematics, trust in colleagues, and the courage to build machines the size of cities in pursuit of a subatomic whisper. In 2013, just 1 year after the discovery, Peter Higgs and Francois Englert were awarded the Nobel Prize in Physics. Higgs famously missed the initial phone call he had gone for a quiet walk to avoid the media frenzy. He later reflected on the discovery with characteristic humility. It's very nice to be right sometimes, but the truth runs deeper. The Higgs boson is not just right, it's a cornerstone of reality, a silent architect, shaping the mass of every atom in your body, every star in the sky, every planet, galaxy, and black hole. When you lift your hand, when you walk, when you breathe, you interact with the Higgs field. The universe is built on invisible scaffolding, and for the first time in history, humanity identified a piece of that scaffold. The discovery didn't answer every question, but it confirmed that the universe is, at its core, surprisingly understandable and astonishingly beautiful. The hunt for the Higgs boson began as a theoretical puzzle, grew into a global mission, and ended in one of the greatest scientific triumphs of the modern era. Yet the excitement continues. Every new collision at the LHC has the potential to reveal something unexpected. A dark matter particle, a symmetry-breaking anomaly, a hint of new dimensions. The Higgs opened the door, but we are only beginning to step through it. And so the story of the God particle is not finished. It is alive, ongoing, unfolding with every proton that slams into another at nearly the speed of light. It is the story of our universe and our quest to understand it, no matter how difficult, no matter how long it takes. The Higgs boson was once a ghost in the machine. Now it is a beacon, guiding us toward the next frontier of physics. The hunt took 40 years. The next chapter may take longer. But if history has shown us anything, it's that the universe always rewards those brave enough to chase its deepest secrets.